Welcome back. In the last video, I left off leaving the challenge of recreating this model here. It's not too difficult to do. We've got 2 hidden layers and 5 neurons. We've got our data set, which looks kind of like ours. But the main points here are have to learning rate of 0.1, which is what we've been using. But to change it from, we've previously used a linear activation. To change it from linear to ReLU, which is what we've got set up here in the code. Now, remember, ReLU is a popular and effective nonlinear activation function. And we've been discussing that we need nonlinearity to model nonlinear data. And so that's the crux of what neural networks are. Artificial neural networks, not to get confused with the brain neural networks, but who knows? This might be how they work too. I don't know, I'm not a neurosurgeon or a neuroscientist. Artificial neural networks are a large combination of linear, so this is straight, and non-straight, non-linear functions, which are potentially able to find patterns in data. And so for our data set, it's quite small. It's just a blue and a red circle, but this same principle applies for larger data sets and larger models, combined linear and non-linear functions. So we've got a few tabs going on here. Let's get rid of some. Let's come back to here. Did you try this out? Does it work? Do you think it'll work? I don't know. Let's find out together. Ready? 3, 2, 1. Look at that! Almost instantly, the training loss goes down to 0 and the test loss is basically 0 as well. Look at that. That's amazing. We can stop that there. And if we change the learning rate maybe a little lower, let's see what happens. It takes a little bit longer to get to where it wants to go to. See, that's the power of changing the learning rate. Let's make it really small. What happens here? So that was about 300 epochs. The loss started to go down. If we change it to be really small, oh, we're getting a little bit of a trend. Is it starting to go down? We're already surpassed the epochs that we had. So see how the learning rate is much smaller? That means our model is learning much slower. So this is just a beautiful visual way of demonstrating different values of the learning rate. We could sit here all day and that might not get to lower, but let's increase it by 10x. And that was over 1,000 epochs and it's still at about 0.5, let's say. Oh, we got a better, oh, we're going faster already. So not even at 500 or so epochs, we're about 0.4. That's the power of the learning rate. We'll increase it by another 10x. We'll reset, start again. Oh, would you look at that? Much faster this time. That is beautiful. Oh, there is nothing better than watching a loss curve go down. In the world of machine learning, that is. And then we reset that again. And let's change it right back to what we had. And we get to 0 in basically under 100 epochs. So that's the power of the learning rate. Little visual representation. Speaking of learning rates, it's time for us to build an optimizer and a loss function. So let's write here. We've got our nonlinear model. Set up, loss, and optimizer. You might have already done this because the code, this is code that we've written before, but we're going to redo it for completeness and practice. So we want a loss function. We're working with logits here, and we're working with binary cross entropy. So what loss do we use? Binary cross entropy. Sorry, we're working with a binary classification problem. Blue dots or red dots. Torch.optim. What are some other binary classification problems that you can think of? We want model 3. Dot parameters. They're the parameters that we want to optimize this model here. And we're going to set our LR to 0.1, just like we had in the TensorFlow playground. Beautiful. So some other binary classification problems I can think of would be email, spam or not spam, credit cards, so equals fraud or not fraud. What else? You might have insurance claims equals who's at fault or not at fault. If someone puts in a claim speaking about a car crash, whose fault was it? Was the person submitting the claim, were they at fault? Or was the person who was also mentioning the claim, are they not at fault? So there's many more, but they're just some I can think of off the top of my head. But now let's train our model with nonlinearity. Woohoo! Oh, we're on a roll here. Training a model with nonlinearity. So we've seen that if we introduce a nonlinear activation function within a model, remember this is a linear activation function, and if we train this the loss doesn't go down. But if we just adjust this to add a ReLU in here, we get the loss going down. So hopefully this replicates with our pure PyTorch code. So let's do it, hey? So we're going to create random seeds. Because we're working with CUDA, we'll introduce the CUDA random seed as well. Torch.manual seed. Again, don't worry too much if your numbers on your screen aren't exactly what mine are. That's due to the inherent randomness of machine learning. In fact, stochastic gradient descent, stochastic again stands for random. We're just setting up the seeds here so that they can be as close as possible, but the direction is more important. So if my loss goes down, your loss should also go down on target device. And then we're going to go xtrain. So this is setting up device agnostic code. We've done this before, but we're going to do it again for completeness, just to practice every step of the puzzle. That's what we want to do. We want to have experience. That's what this course is. It's a momentum builder, so that when you go to other repos and machine learning projects that use PyTorch, you can go, oh, does this code set device agnostic code? What problem are we working on? Is it binary or multi-class classification? So let's go loop through data. Again, we've done this before, but we're going to set up the epochs. Let's do 1,000 epochs. Why not? So we can go for epoch in range epochs. What do we do here? Well, we want to train. So this is training code. We set our model3.train. And I want you to start to think about how could we functionize this training code. We're going to start to move towards that in a future video. So one is forward pass. We've got the logits. Why the logits? Well, because the raw output of our model without any activation functions towards the final layer, classified as logits or called logits. And then we create ypred, as in prediction labels, by rounding the output of torch.sigmoid of the logits. So this is going to take us from logits to prediction probabilities to prediction labels. And then we can go to, which is calculate the loss. That's from my unofficial PyTorch song. Calculate the loss. We go loss equals loss fn, y logits. Because remember, we've got BCE with logits loss and takes in logits as first input. And that's going to calculate the loss between our model's logits and the y training labels. And we will go here, we'll calculate accuracy using our accuracy function. And this one is a little bit backwards compared to PyTorch, but we pass in the y training labels first, but it's constructed this way because it's in the same style as scikit-learn. 3, we go optimizer 0 grad. We zero the gradients of the optimizer so that it can start from fresh, calculating the ideal gradients every epoch. So it's going to reset every epoch, which is fine. Then we're going to perform backpropagation. PyTorch is going to take care of that for us by calling loss backwards. And then we will perform gradient descent. So step the optimizer to see how we should improve our model parameters. So optimizer.step. Oh, and I want to show you, speaking of model parameters, let's check our model3.stateDict. So the ReLU activation function actually doesn't have any parameters. So you'll notice here, we've got weight, we've got bias of layer 1, layer 2, and a layer 3. So the ReLU function here doesn't have any parameters to optimize. If we go nn.relu, does it say what it implements? There we go. So it's just the maximum of 0 or x. So it takes the input and takes the max of 0 or x. And so when it takes the max of 0 or x, if it's a negative number, 0 is going to be higher than a negative number. So that's why it zeroes all of the negative inputs. And then it leaves the positive inputs how they are, because the max of a positive input versus 0 is the positive input. So this has no parameters to optimize. That's why it's so effective, because you think about it, every parameter in our model needs some little bit of computation to adjust. And so the more parameters we add to our model, the more compute that is required. So generally, the kind of trade-off in machine learning is that, yes, small parameters have more of an ability to learn, but you need more compute. So let's go model3.eval, and we're going to go with torch.inference mode. If I could spell inference, that'd be fantastic. We're going to do what? We're going to do the forward pass. So test logits equals model3 on the test data, and then we're going to calculate the test pred labels by calling torch.round on torch.sigmoid on the test logits. And then we can calculate the test loss. How do we do that? Equals loss fn on test logits versus y test. And then we can also calculate the test accuracy. I'm just going to give myself some more space here so I can code in the middle of the screen. Equals accuracy function on what? We're going to pass in y true equals y test. And then we will pass in y pred equals test pred. Beautiful. A final step here is to print out what's happening. Now, this will be very important because, one, it's fun to know what your model's doing, and two, if our model does actually learn, I'd like to see the loss values go down and the accuracy values go up. As I said, there's nothing much more beautiful in the world of machine learning than watching a loss function go down, or a loss value go down, and watching a loss curve go down. So let's print out the current epoch, and then we'll print out the loss, which will just be the training loss, and we'll take that to 4 decimal places, and then we'll go accuracy here, and this will be acc, and we'll take this to 2 decimal places, and we'll put a little percentage sign there, and then we'll break it up by putting in the test loss here, and we'll put in the test loss, because remember, our model learns patterns on the training data set and then evaluates those patterns on the test data set. So, and we'll pass in test acc here. And no doubt there might be an error or two within all of this code, but we're going to try and run this because we've seen this code before, but I think we're ready. We're training our first model here with non-linearities built into the model. You ready? 3, 2, 1, let's go. Oh, of course. Module torch CUDA has no attribute manuals are. Just a typo. Standard manual. There we go. Had to sound that out. Another one. What do we get wrong here? Oh, target size must be same as input size. Where did it mess up here? What do we get wrong? Test loss, test logits on y test. So these two aren't matching up. Model 3 X test and Y test. What's the size of... So let's do some troubleshooting on the fly, hey? Not everything always works out as you want. So length of X test, we've got a shape issue here. Remember how I said one of the most common issues in deep learning is a shape issue? So we've got the same shape here. Let's check test logits.shape and y test.shape. We'll print this out. So 200, oh, here's what we have to do. Well, that's what we missed, dot squeeze. Ah, see how I've been hinting at the fact that we needed to call dot squeeze? So this is where the discrepancy is. Our test logits.shape, we've got an extra dimension here. And what are we getting here? A value error on the target size, which is a shape mismatch. So we've got target size 200, must be the same input size as torch size 201. So, did we squeeze this? Oh, that's why the training worked. Okay, so we've missed this. Let's just get rid of this. So we're getting rid of the extra 1 dimension by using squeeze, which is the 1 dimension here. We should have everything lined up. There we go. Okay, oh, look at that. Yes! Our accuracy has gone up, albeit not by too much. It's still not perfect. Ideally, we'd like this to be towards 100% and the loss to be lower. But I feel like we've got a better performing model. Don't you? Now, that is the power of nonlinearity. All we did was we added in a ReLU layer, or just 2 of them. ReLU here, ReLU here. But what did we do? We gave our model the power of straight lines. Oh, straight linear. Of straight lines and non-straight lines. So it can potentially draw a line to separate these circles. So in the next video, let's draw a line, plot our model's decision boundary using our function, and see if it really did learn anything. I'll see you there.